And once again we're here for Advent of Code 2024. In the last video we looked at the first challenge on day 5, so today we're going to look at the second part, and I'm tackling these programming challenges in Funciton, my esoteric programming language that uses Unicode box drawing characters to create lines and boxes. Now in the last challenge we were given a number of criteria according to which a set of integers need to be sorted, but the challenge didn't tell us to reorder those integers. It simply said try to find the ones that are already in the correct order. At the end of that video I gave my guess as to what the sequel challenge would be, and I said maybe this time we actually need to reorder them. So, let's see if I was right. Part 2. While the elves get to work printing the correctly ordered updates, you have a little time to fix the rest of them. Looks like I was right. For each of the incorrectly ordered updates, use the page ordering rules to put the page numbers in the right order. Bingo. For the above example, we just change the order. And then we still need to extract the middle page numbers. This was part of the challenge on the last day. They are highlighted here. And then we add them all up, and that would give us 123 in this example. Now, I was kind of dreading this because initially I didn't really have a good idea on how to do this in Funciton. But since this was my guess for the second part, I've had enough time to think about what I would do. And the main reason I was unsure is because the only sort functions we've written so far in Funciton are this one here, which literally just sorts integers, and this one here, which takes a selector, in other words, a function that will transform every element to a new element and then sort by that, while retaining the original elements. But a lot of programming languages, including JavaScript, have a sort function which takes a compare function, which is not something that modifies each element, but rather it takes two elements, and then it tells you which order those two elements should be in, which one should come before the other. And the idea here is that the compare function will return something that is either negative, to indicate that A and B are already in the correct order, or 0, to indicate that the order doesn't matter, or positive, to indicate that B needs to come before A. And that's kind of perfect for our example, because this is basically a list of things that this function needs to return. Every time it's given 47 and 53, it needs to return -1 to indicate that's the correct order. And every time it's given 53, 47, it needs to return 1 to indicate that they need to be swapped. For any pair of integers that is not in the list, it would just return 0. But of course that means that we need a new sort function, one that takes such a comparison function instead of a selector. So, I'm going to start with that. And I've decided to use the existing sort function that uses a selector and see if I can modify it. Now, if you remember my video for day 1 of Advent of Code, I explained that the sort function works by taking the first element of the list, and we take all the elements that are smaller than that, then we take that element, and then we take all the elements that are greater or equal to that. So that basic principle is still going to stay the same, except that this time we are going to use the comparison function, and we're going to pick all of the elements where that gave us -1, put that in front, then add that element, and then have all the rest of them where the function gave us something that is 0 or positive. So let's see how much of this function we can reuse. The first thing, of course, it checks if the sequence is empty. If it is empty, then we just return an empty sequence. We don't need to sort anything. But if it is not empty, then we need to concatenate two parts. On the left side, we have the first bunch of numbers, which of course go through the recursive call so that they are now sorted. And you can see here that we use the filter function to find all the elements that are smaller than the pivot after being run through the selector. So instead of calling that selector here, we're going to need to use the comparison function. On the other side of that concatenation, we first need to add the pivot to the front of it. Because remember, we want to put the pivot in between the two bunches, and the way we do that is we add it to the front of the second bunch, and then we concatenate the two. But long story short, here we have the second recursive call, which sorts the second bunch, and of course the second bunch is filtered, again by the same selector, but this time we're checking if it's greater or equal to instead of less than. I assume that the order of operations is different there. So how much of this can we keep the same? Well, we want to keep the concatenation, we want to keep the recursive calls, and we want to keep both of the filters. The only thing that's different is what we filter by. Okay, our input sequence goes in here. If it's empty, we still return 0. And if it's not, we want to concatenate the recursive call. and we want to filter the original sequence. No, not the entire original sequence, just the tail of that sequence, because remember the head of the sequence is the pivot. And the second argument to the recursive call is the same comparison function that we're going to need in a second. Let's take a quick look at the other filter function. We don't need this wire crossing function here right now. So the first argument to this filter is going to be the same as this one here, so it's the tail of the sequence. And what goes in here is the pivot, which is the head of the sequence. I'm just going to put head because there's not enough space there, but we know it's the head of that sequence. I can now see why there was a wire crossing function here, so I'm quickly going to restore that. Now let's write the first filter here. If this is where the lambda expression comes out, then this is the input. And remember, we're comparing the pivot against that, so I'm going to call this b. And what we want to pass into here is a boolean determining whether or not to filter this in. And we want to filter this in if b should be first. So we need to check for greater than 0. And the thing that needs to be greater than 0 is the result of the function that we're passing in. But remember that this time this function is a 2-input function, so we need 2 invocation boxes. The thing that goes into the greater than sign is the first output of those. We don't care about the second output, so let's silence those. The function that we're actually calling is fn, and the first argument we want to pass in as the pivot, which is the head of the sequence, and the second one is b. Now b occurs down here, so I'm quickly going to add a wire crossing function to put that in there. Okay, so much for the first lambda expression. Now let's do the second one, where we need to do basically the same thing, but because of the geometry, the way that this is laid out, we need to rotate this by 90 degrees counterclockwise. But this time we don't want greater than 0, we want less than or equal to 0. Now there are 3 occurrences of head, so let me join those up. And then let's use wire crossing functions to connect up the tails as well. And now we can obtain the head and the tail by calling the input sequence. Now let's make a declaration box and join up the places where we need the sequence. And finally, the 3 places where we need the comparison function. So if I haven't made a mistake, then that should be it, except that we still need to change the recursive calls to use the new function name. And then I can compactify the function a little bit. And now let's put that function in the library, and then let's quickly test it. So let's write our typical program where we obtain the standard input, split it at the commas, convert every string to an integer, then run that through the sort function that we just wrote, and I'm going to use a minus b as the comparison function because that's what people usually use in JavaScript to sort by numbers. Then convert all of the numbers back into strings, and then join it with commas for output. Alright, let's see if my test program works on an input string with just a single number. It should just output a 1, and of course it doesn't. So let's take a look at this. It points at line 300, character 31, and it turns out that is this position here. And indeed, this was supposed to turn the input sequence into a head and tail. And I put a lambda expression there instead of an invocation. So I think I just need to change that to an invocation box, and then we should be golden. So let's run the same thing again. Ooh, invalid. Ooh, okay. Lambda number 44, which is a comma. Yep, that's in the example program where I got the operands on the join function wrong. The first argument is supposed to be the sequence, which is this one here, and then the separator. So all I need to do here is just switch the output to the other side. So let's see what happens now. And we get a 1. Now let's put some random numbers in some random order. And hopefully we get a sorted list, and indeed we do. So I think this works. Now to be fair, we haven't fully tested the capability of the comparison function, because we're just sorting integers. But I think if there is a bug in this, it would be quite a coincidence if it happened to work correctly. So I'm going to move on and write the actual program. Now this here is the solution that we had for the first part of this day. And I think I can salvage some of this. We start with the standard input here and we split it at the double new line. And then we separate each line in each of the inputs by the new lines. And we're also converting that first bunch of input, the one with the number pipe number, into a series of lambda expressions that return just the 2 values, where the first output of the lambda expression is the second number after the pipe and the second output is the first number before the pipe. So I've transferred that part of the program. Now let's annotate what this is. This is the list of, I'm going to call them tuples, but they're pairs, right? There are 2 tuples. What comes out of here is a list of integers which represent the page numbers in a batch. So let's call them the page numbers. And what we want to pass into here is the middle page number, which I'm just going to call mid, but only for the ones that aren't already sorted. Now the logic to calculate the middle page number, I can copy that as well. But now the condition on this question mark needs to be different. Previously we used a regular expression to check whether it is already in the correct order. But this time I'm just going to sort all of them, and I'm going to check if the sorted list is the same as the original list. And for that I already have a function, which is called equal appropriately, which checks if two sequences contain the exact same values or not. So let's put a call to that function here. And curiously, the rest can stay the same, because if they are indeed the same sequence, we want to return 0. In other words, we don't want to count the middle page number. But if they are different, then it means that we had to order them, which means that we do want the middle page number. Now let's pull this apart a bit so we have a bit more space. Now we want the original list of page numbers to be one of the operands on that equals, but we still need to take a copy of it in order to do the sorting. Meanwhile, the other operand to the equals is the same as what we want to put into here to calculate the middle page number, namely the sorted list. So now let's call our new sort function on that list of page numbers. Now the sort function only takes 2 parameters, but the second parameter is that lambda expression with 2 inputs that we need to worry about. The output, of course, goes right in here. Now let me scroll down a little bit. So this is the lambda expression, which means that these are the 2 inputs. So now we need to find a tuple in our list of tuples where either this one is the first and that one's the second, or that one's the second and that one's the first. Now what does our comparison function need to return? Ultimately, of course, we're going to go through the list of tuples, but if there isn't such a tuple, then we want to return 0. So I'm going to pass the tuple in here, and if it's 0, then we will return the 0. Now our sort function definitely doesn't care about the second outputs of those lambdas, so let's quickly put a 0 there. Now let's assume that we have a tuple. We now need to return 1 or -1 depending on whether the tuple is in the correct order. And the condition on this question mark is whether the first value is equal to the first output of that tuple. So we need an equal sign, which in turn is a boolean, so we can change the question mark to an interrobang. Now let's give these values a label. Let's say this one here is value A and this one here is B. But I want to give the values in the tuples names as well. So I'm going to call these y, x because the puzzle refers to the x pipe y thing. But remember that we are actually swapping the order. So the first element in the tuple is actually the second number after the pipe. So that means they are in the correct order already if A is equal to X or B is equal to Y. We only need to check one of those two. But in that case, the 1 and the -1 need to be the other way around. Now, how do we find the correct tuple with the X and Y values that we need? We need to find a tuple that is either A, B or B, A. And I'm going to use the filter function to find the tuple that we need. I assume there's going to be only one, but even if there are multiple, it doesn't matter, because then I'm going to use the first or default, which will either give me the first tuple that it finds, or if none of the tuples match, then I can specify my own default value, and I'm gonna use 0, so that this question mark here will see that as a false. Now it's getting quite inconvenient here because there is not much space here, so I'm going to turn that into a function that will return me the tuple that I want. So let's join this all up into a single function call. And now let's write that function, but let's try to keep track of the order in which we're passing these in, because this order is a little weird. We're passing in B first, then A, and then the list. So our declaration box will look something like this. And like I said, I'm going to obtain the tuple that I need using the first or default function. And if the tuple doesn't exist, the default value should be 0. But to find the correct tuples in the first place, we need a filter function. And the filter function needs a lambda expression, and the filter function doesn't care about the second output. The thing that is passed into the lambda expression is one of those tuples, and we want to keep that tuple if one of two possibilities is the case. Either A is equal to X and B is equal to Y, or A is equal to Y and B is equal to X. So we need a boolean OR. And now each of those two conditions that we want to OR together is itself an AND, right? It's A equals X and B equals Y on one side. And the Boolean negation for the AND will conveniently cancel out with the one for the OR. So now there are 8 connectors on all of these equals that we need to fill. 2 of them need to be A, 2 of them need to be B, 2 of them need to be head, and 2 of them need to be tail. So I'm going to make it convenient for myself by just putting A right here. And that means I need to compare it with something here and something here. I'm going to arbitrarily say this is the head and this is the tail, but I might swap them around later if it becomes more convenient. Now that means that this one here needs to compare B against the head. I'm going to put the head here, and then that means this is the tail, so that I can put the B's on the outside. Now this will allow me to connect up A and B. It only just occurred to me that these are not head and tail, these are X and Y, my apologies. So now let's split the tuple into X and Y by calling it. Remember that Y is the value that comes out of the first output. Now I can pass one copy of X and Y into here by using lots of wire crossing functions. Meanwhile, I can pass the other copy of X through the middle of that line, and the other copy of Y, I'm just gonna move that around the bottom of the function. And finally, we just need to put the list in the right place. So, if I haven't made a mistake, this function will extract the tuple that we need. Now coming back to the main program, that tuple now comes out of here, and we still need to perform this equals operation in order to determine which way round the tuple is. Now since the value B is the lower one of these two wires, I've decided to go with the B equals Y thing. Now let's put a Y crossing function here, and let's pass the B into the equals function. But in order to get the Y, we need to turn the tuple into X and Y, but we also need the tuple here, so let's quickly take a copy of it. And now let's invoke the tuple to extract the two values. Now the tuple goes in here, which means this is the input, and the tuple doesn't care about the input, so I'm actually just going to reuse that 0 box that we already have up there. And then the first output from this box is going to be the Y that we need, which means that I'm going to ignore the second one. And then we can get rid of these annotations here. Alright, so now, if I haven't made a mistake, our map function will return the list of the middle page numbers that we want to sum up. So just as last time, I'm going to use the sum function and then convert the result to a string for output, and then let's run that program. As before, I'm going to run it on the example input first, the one that's given in the puzzle description page, and I'm getting 123. And on the puzzle page, it says that that is the correct answer. So it looks like we have a potentially working program. So let's run the same program with time measurement this time on the full input and see if that works. And I'll come back to let you know when it's finished. Good morning, it's a new day. I forgot to mention yesterday that the -m option on the Funciton interpreter, its purpose is to tell you how long it took. But I actually extended it so that now it gives you not just the time taken, but also the amount of memory that was used and the number of lambda expressions created. If you remember the lambda expression video, the Funciton interpreter allocates numbers starting from 1 to each lambda expression created. So you can see that it took quite a while, so long in fact that I didn't expect I would need to format this in hours and minutes. Now, this is actually 13 hours and 9 minutes. Wow. Now, long story short, let's actually take a look at this answer that we got and see if it's correct. So let's go back to the puzzle page and paste it right here and press enter. And that's the right answer! You are 1 gold star closer to finding the chief historian. And it only took 13 hours and 9 minutes of full-time computation. Now, as for the memory usage, I actually looked at that in Task Manager while it was running, and it actually got up to 31.5 gigabytes according to Task Manager, which happens to be just under 32 gigabytes, which is the amount of RAM I have in my PC. So I think it stands to reason that this number only includes physical RAM used and not virtual memory. So it's very likely that it actually used even more than 30 gigabytes, and it's just not counting all the data that it swapped out into virtual memory. Okay, so I technically solved the problem, right? But I'm not really happy with having a program that runs for multiple hours and takes up all of my RAM. I mean, that's ridiculous. So I sat down to think about what I would need to do to fix this. Now, if you've been following my channel in chronological order, then you know that I made this video in the meantime. Arrays. You see, everything you've seen up to this point, I did before that. And it's because of this result of taking hours to complete and using tens of gigabytes of RAM that gave me the impetus to think about that. Now, I think the main reason this program uses such a ridiculous amount of memory is because it keeps allocating lambda expressions while it runs. In particular, you remember that this function uses a filter to filter the list of pairs of integers, and it does that over and over again for every single pair of integers within each of the comma-separated strings. So I think I can significantly improve upon that, first, by not using lambda expressions quite so much, and two, by making use of the algorithm that I implemented in that arrays video, binary search. So here's what I'm going to do. Remember that what comes out of here is the first part of our input, and then we're splitting that at the new line so we get each line of text as a separate string. And then we're mapping over that to split each of those strings at the pipe character. I am not going to do that anymore. Instead, we're just going to take that list of strings and we're just going to turn that into a sorted array. So what's going to go into this function here is going to be that sorted array. So let's start by rewriting this function in such a way that we can properly make use of binary search. Let me basically delete that entire function, and then let's label the three inputs. Now remember that A and B are actually strings, and the array is going to be an array of strings which still have the pipe character in them. So what I'm going to do is I'm going to concatenate A and B with a pipe character in between them, and that will give me a string that I'm looking for in that array. And I can use binary search for that. So let's start by writing our first condition. And my first condition is that A pipe B is in the array. And we're going to use binary search for that. Now the binary search function has two outputs, the first one of which is the boolean, which determines whether the element was in the array. And since that's a boolean, we can just use the interrobang function here. The second output is the index in the array at which the element was found, and we don't need that, so let's just silence that. The first input to the function is the array, and the second input is the element that we're looking for. And that element that we're looking for is either A pipe B or B pipe A. Let's start with A pipe B, so we need to concatenate them up. Now I could either do A and then pipe concatenated with B, or I could do A on this side and then have the pipe character concatenated with B on this side. I've decided to put the pipe character over here. Now, what if that value is in fact found in the array? What do we want to return? Well, let me scroll up to the previous function that we had, and you'll remember that we were returning 1 or -1 depending on whether we want those elements to be this way or that way around, or 0 if we don't know, if we don't care. Instead of deciding that value up here, I'm just going to return the correct value from that question mark right away. And in this case, we were looking at A pipe B, which means that A and B are already in the correct order, and in that case, we want to return -1. What about the else branch? Well, we now know that A pipe B is not in the array, but what about B pipe A? If B pipe A is in the array, then we need to swap them during the sort, and we want to return 1 instead of -1 for that. So we need to do the binary search a second time. Once again, we're only interested in the boolean that says whether the element was found in the array, so we can silence the other output that returns the index in the array. And then we have the array, and then we need B pipe A, so we need another concatenation. Okay, this time, if the binary search algorithm finds our element, we want to return 1. And if the element is still not found, in other words, the second else branch, well then we return 0. And then we need to join up all of those lines with the declaration node at the top. Alright, if I haven't made a mistake, we now have a function that returns the -1 and 1 for us, which means that our main program doesn't need to do all this anymore. So I'm just going to delete all that, and I'm going to pipe the output of that circle3 function directly into the output of the lambda for the sort function. Now this could certainly be more elegant, but I'm going to leave it like this because it's not going to save any space moving this around. So I said that I'm going to put a sorted array into here, so I most definitely don't need this map function anymore. Now in that arrays video, I wrote a function that can just turn a lazy sequence into an array. So I could just take this lazy sequence here and sort it first, and then turn that into an array. But I also hinted in the video that I wanted to write a function that will create a sorted array straight away, by just using binary search each time to know where to insert each element. So, I'm going to do that now. As a reminder, this is the function that we wrote in the arrays video, which will convert a lazy sequence to an array, and we always use the index 0 to insert every element at the start, so we're constructing the array from back to front. But now instead of the 0, I want to call the binary search function and use the index that it returns. Remember that even if the element is not in the array, the binary search function will give us the index where we need to insert that element in order to maintain sortedness. So let me start by renaming the function and changing the comment. And then let's change that 0 to an invocation of the binary search function. Now this time we're interested in the index, which is the second output of the binary search function, which means that the first output we don't care about. We want to silence that, so I'm going to put the flag there. The first input to that binary search function is the array into which we want to insert, which is of course the array that we're inserting into. So I need to take a copy of the result of that recursive call and put that into that binary search function. And finally, the last input to the binary search function is the element that we're looking to insert. And, well, that's of course the same element that we're passing into the insert function. So let me just quickly take a copy of that. And then let me compactify the function again. Alright, that's looking pretty good, but let's test it. Now I still have the last test program from the arrays video. All I'm going to do is I'm just going to remove this, I'm going to do this, and I'm going to change that function to this function, and then just fix up the connectors to the toString function. And that gives us a program that will take our standard input, it will split that at the commas, and that gives us a list of strings, and then we use the map function to turn that into a list of integers, and then we pass that into the new function that we just wrote. So what should come out of that is a sorted array if we haven't made a mistake. And then we're turning that into an integer so that we can see the number on the command line. Okay, so let's start with an easy one where the array is already sorted, and I'm going to pipe that directly into my base converter to convert it from decimal directly to binary. So we are looking at a sign bit, a continuation bit, and then 21 bits of payload, which tells us the number of bits in each element within the array. So that is a 3 in this case. And then this is the stop bit. All of that is the variable length encoding for tuples, which we got from the lists video. Everything after that is the array, and all that this does is tells us that everything after that will come in chunks of 3 bits. The first 3 bits, which are these, well, this encodes the number 2, which is 1 less than the number of elements in the array. So the array actually contains 3 elements. And here's the first element, and this is a sign bit of 0, which means it's a positive number, and the number 1. And then we have another sign bit and the number 2, and then another sign bit and the number 3. So far, this seems to be working. Now, let's do the exact same thing, but with the numbers in a different order. For example, 3, 1, 2. I expect to get exactly the same result, and it turns out that I do. So now let's try something a little more adventurous. I'm just going to bang the keyboard here a little bit and just type some random numbers in some random order. And now I expect an array with obviously a bigger bit size than 3, because these numbers are bigger than 3 bits. Well, it turns out that we have 8 bits. So this is the stop bit after the variable length encoding, and then we want 2, 4, 6, 8 bits. So this will be the number of elements in the array, and indeed it gives us a 3, which is 1 less than 4, so we have 4 elements. And then we have this, these are the next 5 bits, and as you can see, that encodes the number 2 if you take out the sign bit. The next 8 bits are these. Again, the sign bit is 0, which means it's a positive number, and this time we have 1, 2, 4, 8, 16, so that is a 19. That is correct, that is what we expect. We expect the next one to be a 25, so again we have a sign bit, and then we have 7 bits of payload. We have 1, 2, 4, 8, and 16. 8 plus 16 is 24, plus the 1 is 25. And then finally we have a sign bit, and then we have this big number here, which I can just convert. I'm just too lazy to calculate it. There you go, it gives us 74. So now that we have that, we can come back to our Advent of Code program, and we need to insert a call to that new function right here in order to generate the sorted array. And that should be it. Let me see if I can get the entire program on the screen. Now looking back at the Advent of Code puzzle page, just to remind us that the answer that we expect from the example input was 123. So let's run this new version of my solution using that example input, and we should get 100. We get 123. Awesome! But now we want to run it on the full input, and we want to know how long it takes and how much memory it uses. So let's run that. And what do you know? We took it down from taking hours to taking 3 minutes. What an improvement! And I can also confirm that it gave the right answer, the same answer that I've already submitted. And on top of that, we've used only 4 gigabytes of RAM, which is still a lot, but A, it's not 30 gigabytes, and B, the main reason it's still that much is because we're still using a lot of lambda expressions, especially for the sort function. In theory, we could implement a sort function on arrays, which would replace the elements in place, so you wouldn't need to keep calling lambdas. But I think this video has gotten long enough, so I'm gonna stop it here, and I'm going to move on to day 6 of Advent of Code 2024 in the next video.